Hey everyone, I'm Nick, and welcome to another episode of Parallel C++. So in this episode of the series, we're going to be talking about the nowait clause in OpenMP. So our parallel programs often need some form of synchronization, and we've seen a number of ways that we can get this. So we've seen how we can serialize access to some resource using a critical section, and we've also seen how some of our other directives, so things like our single and our for directive, both include some inherent synchronization, right, at the end of the blocks, right, at the end of a single block or at the end of a OMP4 block. Now, synchronization is something inside of our parallel programs that we often want to use sparingly, right? Synchronization has an inherent cost. We're waiting for threads to, say, communicate with each other in some way. So we try to remove this, right, whenever we can, right, for better performance. So what we're going to be looking at today is a way that we can mark that we don't want some of our directives to include this inherent synchronization, and we're going to use our parallel Gaussian elimination that we looked at last time as an example of this and see how we can squeeze out a little bit of extra perf by doing some slight modifications to our code. So let's go ahead and get started, and let's do a bit of refresher on our parallel Gaussian elimination from the last video. So here we're using Google Benchmark again to time our code. And this is going to be our timing loop where we're going to do Gaussian elimination on some matrix that we're copying in each iteration. So inside of our code, right, we have this big parallel section where we spawn a group of threads, and all of our threads will work together to do Gaussian elimination. So one thread, right, in this pragma OMP single block here will end up, right, doing the calculations for, right, each row. And then all of our threads work together in this parallel for loop down here to do the elimination for the pivot elements for the remaining rows inside of the matrix. So that's what this loop is doing down here. And then each iteration of the loop, one of our threads updates the row that we're working on by one, right? We move on to the next row. Okay, so let's think about where we have synchronization points in this program. So as we looked at last time, we have a synchronization point at the end of our single block down here. So you can see down here in the clauses section of this Lawrence Livermore National Lab tutorial on OpenMP, specifically looking at the part on the single directive, it says that threads that in the team that do not execute the single directive wait at the end of the enclosed code block unless no wait clause is specified here. So while one thread is doing the work in here, the rest of our threads wait right after this block for our single thread to finish. So we have a synchronization point here. Now likewise, the same is true for our pragma OMP4. So if we go ahead and take a look at similar documentation for our for directive, and we look at the clauses down here, we see that we also have this no wait clause that we can specify. So that we can say that threads do not synchronize at the end of this parallel loop. So by default, right, our threads will all work together to perform iterations of this loop, but when they all finish, they wait for the other threads, right, at the end of this block down here. So there we have another synchronization point. And then we have, right, our final synchronization point here with our final single block. One thread does this update, our other threads wait for our single thread to do this update. So let's see where we might be able to get rid of, a synchronization point in this code. So we'll start from the very top here. So we have our calculation of our, pivot row here, the row that we're working on, right, on this iteration. So here, right, we need to make sure that our threads wait, right, for this calculation to finish because we're going to be using elements from this row in the later calculation. There may be some ways that, we can be somewhat clever and start our threads in the elimination, right, before, this calculation completes for the entire row, but that might be a little bit difficult. So we'll leave that alone for now. Then we see that we have, right, another bit of synchronization here after for. So really there's no dependency between each of our threads here, right, when we're doing this elimination. They're all just reading, from this row that we did some calculations on in the previous section and subtracting it from each row's mapped rows for elimination. And then our final synchronization is at this OMP single down here, where we update the row number. So our only real synchronization point or dependency between these two blocks is that we use row, right, for this pragma OMP4, right, in a couple different places. So what we want to make sure that we do is that we don't update row before we're finished using row, right, in this for loop here. But it seems a little silly to potentially have threads wait for synchronization up here right at the end of this pragma OMP4 if all we're really doing is waiting to update a single integer here. There might be a way around this. So let's see how we can get rid of the implicit synchronization that happens at the end of this for loop, right, using and use this nowait clause. So let's go ahead and open up our nowait.cpp. And our code is pretty much exactly the same here. So the exact same setup. We're doing Gaussian elimination on a 2 to the 10 by 2 to the 10 matrix. And we go down here and you can see that we've now specified this for loop as nowait. But how exactly did we get rid of that dependency right between our row that we're updating down here and the one that we're using inside of this parallel for loop? Well, the way that we're going to do this is by using a little bit of extra memory and keeping track of two integers, right? Our current row and our next row. So on every single iteration of the loop, right, when we're first doing our row calculation, we're going to set our current row equal to the next row up here. So we're going to be using this current row throughout the remainder of this loop. So here, right, all throughout, when we do the pivot row calculations and when we do the eliminations, we're just working with this current row variable, right? Then when we do the update on each iteration, we're going to update next row, right? That way we don't interfere with the current row that's being read inside of this parallel loop. That way we can mark this for loop as nowait. So as soon as threads complete, they can, just move on past this for loop and one of our threads can eventually go, into this, pragma OMP single block down here while the rest of our threads wait, right? Because we do have another synchronization point down here. And the only time that we update current row is once we get back around in this loop and look at this, we get back to this pragma OMP single block. But that's already after we have a synchronization after this other single block at the end of our loop here, where we're updating next row, right? So then we just go around the loop again, right, and update current row equal to next row. But now we've made it so we were able to get rid of this inherent barrier, right, at the end of this pragma OMP for loop, right, and hopefully get us some more performance here by not doing unnecessary synchronization. Synchronization can be somewhat expensive. So let's go ahead and see, what this bought us performance-wise. So let's compile both of these applications. So we'll start by compiling 0 baseline and then compile our nowait example here. Now both of these are compiled with the exact same flags. So turn on OpenMP with -f OpenMP, and then of course use O3 optimizations. And because we're using Google benchmark, link against libbenchmark and libpthread. Okay, so let's go ahead and time both of these. So we'll go ahead and start by running our baseline example here. And we see that it takes somewhere on the order of 16.3, 16.4 milliseconds. Now let's see how fast our nowait example is. And we can see that it's a decent amount faster here. So we're somewhere between 15.6 milliseconds or so faster. So this is a savings of around 0.7 milliseconds. So it's a little bit of time, but all we really had to do there was introduce a new integer. So that's a pretty good performance improvement by just understanding when we need actual synchronization and getting rid of synchronization when we don't need it using this nowait clause. Okay, so that's going to go ahead and do it for today. As I mentioned, this nowait clause can be applied to a number of our directives here. So for example, we can add it to this for directive, but it can also be added to this single directive so that threads don't wait at the end of the single block, right? And when we use this depends on our specific circumstances and when we can actually get around the synchronization. But that's going to go ahead and do it for this time. As always, you can find this or any of my other examples at github.com/coffeebeforearch under this parallel CPP repository. But that's going to go ahead and do it for today. As always, I'm Nick, and I hope you have a nice day.